They hold the promise of panels that are far thinner and lighter, that could be made with ultra-high throughput at room temperature instead of at hundreds of degrees, and that are cheaper and easier to transport and install. But bringing these materials from controlled laboratory experiments into a product that can be manufactured competitively has been a long struggle. But a new system based on a novel approach to machine learning could speed up the development of optimized production methods and help make the next generation of solar power a reality. The system, developed by researchers at MIT and Stanford University over the last few years, makes it possible to integrate data from prior experiments, and information based on personal observations by experienced workers, into the machine learning process. This makes the outcomes more accurate and has already led to the manufacturing of perovskite cells with an energy conversion efficiency of 18.5%, a competitive level for today's market. The research is reported in the journal Joule, in a paper by MIT professor of mechanical engineering Tony Obuanasisi, Stanford professor of materials science and engineering Reinhold Doskert, recent MIT research assistant Jay Liu, Stanford doctoral graduate Nicholas Rolston, and 3 others. There's always a big challenge when you're trying to take a lab-scale process and then transfer it to something like a startup or a manufacturing line, says Rolston, who is now an assistant professor at Arizona State University. The team looked at a process that they felt had the greatest potential, a method called rapid spray plasma processing, or RSPP. The manufacturing process would involve a moving roll-to-roll surface, or series of sheets, on which the precursor solutions for the perovskite compound would be sprayed or ink jetted as the sheet rolled by. The material would then move on to a curing stage, providing a rapid and continuous output, with throughputs that are higher than for any other photovoltaic technology, Rolston says. Whereas you can think of this approach as more like spray painting. Within that process, at least a dozen variables may affect the outcome, some of them more controllable than others. These include the composition of the starting materials, the temperature, the humidity, the speed of the processing path, the distance of the nozzle used to spray the material onto a substrate, and the methods of curing the material. Many of these factors can interact with each other, and if the process is in open air, then humidity, for example, may be uncontrolled. Evaluating all possible combinations of these variables through experimentation is impossible, so machine learning was needed to help guide the experimental process. So, the team found a way to incorporate such outside information into the machine learning model, using a probability factor based on a mathematical technique called Bayesian optimization. Using the system, he says, having a model that comes from experimental data, we can find out trends that we weren't able to see before. For example, they initially had trouble adjusting for uncontrolled variations in humidity in their ambient setting. But the model showed them that we could overcome our humidity challenges by changing the temperature, for instance, and by changing some of the other knobs. The system now allows experimenters to much more rapidly guide their process in order to optimize it for a given set of conditions or require. Thanks for watching. Please subscribe my channel for more videos.